The centrifuges at the Natanz fuel enrichment plant had been spinning for years without mercy. Deep beneath the Kashan desert of central Iran, in a facility buried under 60 feet of reinforced concrete and ringed by anti-aircraft batteries and armed Revolutionary Guard checkpoints, thousands of aluminum machines worked in continuous, furious rotation. Each one was a marvel of precision engineering, a slender cylinder roughly the height and diameter of a man's midsection, operating at the extreme outer boundary of what physics and metallurgy would permit. The rotors inside those cylinders turned at roughly 1,000 revolutions per second, and the tolerances involved were so fine that a single microscopic imbalance, a flaw invisible to the naked eye, could send a machine into catastrophic vibration and destroy it within seconds. To keep them running, the engineers who tended them had to know their machines with an intimacy bordering on affection. The process those centrifuges performed was ancient in its principle and staggeringly complex in its execution. Uranium hexafluoride gas, fed into the machines at carefully controlled pressures, was subjected to the centrifugal force created by that tremendous rotation. The heavier molecules, containing the more common uranium-238 isotope, were flung outward toward the cylinder wall. The slightly lighter molecules containing uranium-235, the fissile isotope needed for both reactor fuel and weapons, migrated toward the center and rose upward with the inner gas flow. The enrichment achieved by a single centrifuge was minuscule. Only by linking hundreds, then thousands of machines together in linked sequences called cascades, feeding the output of one bank into the input of the next, could the concentration of uranium-235 be gradually increased to useful levels. Low-enriched uranium for reactor fuel required the gas to pass through many stages of this separation. Weapons-grade material required far more. In the final weeks of 2009, something began to go wrong. It started the way the worst disasters always begin, quietly and at the margins, in the slow accumulation of small things that could each be explained away individually but that assembled themselves, over weeks, into something that could no longer be dismissed. A centrifuge in Cascade Hall stopped responding normally to its control inputs. Then two machines in a second cascade began running at slightly off-nominal speeds. By December, the shift supervisor overseeing the night operation was looking at a failure log that made no immediate sense. Machines going offline at intervals that had no apparent pattern, spread across different cascades in ways that defied any single mechanical explanation. The senior staff who gathered in the underground control rooms to review the data brought with them the standard toolkit of nuclear engineering: metallurgical analysis, fluid dynamics calculations, component wear statistics. They were highly trained specialists, educated at Iran's best technical universities and, in some cases, abroad before the revolution changed everything. Several had spent their careers working toward exactly the moment when Iran's indigenous enrichment capability would be proven to the world. They believed in the work with the passionate commitment of people who understood what the political stakes were, and they were not the kind of men who reached for easy explanations when difficult data confronted them. What they found was confusing in a way that made everything harder. The failed centrifuges, when examined by technicians after being taken offline, often showed damage that was technically explicable but statistically alarming. Rotor cracks, bearing failures, where patterns consistent with the machines having been operated outside their design parameters, pushed beyond the speeds or pressures they were engineered to sustain. These were the kinds of failures you might see in a centrifuge that had been run too fast or too hard, or in one that had suffered a sudden pressure spike in the feed gas. Except that the monitoring systems, the instruments and sensors and computer displays that recorded the operating conditions of every cascade, showed nothing abnormal. According to every instrument in the facility, the centrifuges had been running exactly as they should have been running when they broke. Several of the engineers suspected sabotage in the supply chain. Iran had been under severe international sanctions for decades, and the procurement of high-precision industrial components was a complicated process that ran through a labyrinth of front companies, intermediary dealers, and falsified end-user certificates. The frequency converter drives, in particular, were components that had to be sourced with exceptional care. These devices governed the electrical frequency supplied to the centrifuge motors, controlling the precise rotational speed at which the machines operated across their working cycle. A frequency converter that had been built to inadequate specifications, or one that had been deliberately interfered with somewhere along the procurement chain, could cause exactly the kinds of failures they were seeing. The theory was reasonable. It was investigated carefully. It led nowhere definitive. Winter deepened, and the failures continued. The cascades that were supposed to be feeding enriched uranium hexafluoride through the facility's carefully managed production process were instead bleeding machines at a rate no one had projected and no one could explain. The IAEA inspection reports from this period would later be interpreted as confirming what the engineers at Natanz were experiencing from the inside. The number of operational centrifuges at Natanz declined through 2009 and into 2010 in a pattern that did not match the normal attrition of an aging centrifuge park or even an unusually difficult commissioning period. Something was killing the machines. What the engineers could not know, working in their buried facility with its sealed corridors and its scrubbed air and its constant background hum of spinning rotors, was that the explanation for their problems existed in a domain they had not thought to examine. Not in the metal of the rotor casings. Not in the chemistry of the process gas. Not in the procurement chain. The explanation lived in the software, in the invisible digital layer beneath the physical world of the plant, written into the memory of the programmable controllers that governed every cascade in the facility. Someone had placed it there. Someone had reached through the electronic architecture of the facility's control systems with the particular kind of intelligence that could make a machine lie about itself, that could cause damage while simultaneously reporting that everything was fine. The engineers standing in those control rooms, reading their anomalous logs under the pale fluorescent light and drinking the strong tea that was available around the clock in the break rooms off the corridors, were among the first people in history to experience something for which there was genuinely no precedent. A weapon had been deployed against them, a weapon unlike any that had existed before. It had no weight. It left no residue. It could not be detected by any of the radiation monitors that dotted the facility, by any of the chemical sensors, by any of the physical inspection processes the engineers ran when trying to understand why their machines were failing. It had been made entirely of mathematics, of logic, of carefully structured instructions. And it was destroying the physical infrastructure of Iran's nuclear program with a precision that no bomb could have matched and no saboteur could have equaled. The people who made it were thousands of miles away, in offices and laboratories whose locations were highly classified, in buildings that bore no external markings suggesting the nature of the work conducted inside. They had been working on this problem for years. They had studied the target in extraordinary detail. They had built and tested physical replicas of the equipment they intended to attack. And when they finally deployed their creation, they believed they had contained it carefully enough that the world would never know exactly what had happened in those underground halls. They were wrong about that last part. The secret they thought they had kept would be pulled apart by researchers who had never heard of the Natanz facility and who stumbled onto the evidence by accident, in a country that had nothing to do with nuclear programs or strategic weapons policy. But by the time the world understood what had been done, the centrifuges were already scrap. By the time the analysts and journalists and security researchers pieced together the full picture, a new era in human conflict had already quietly begun. The world just did not know it yet. To understand what happened inside that buried facility in the Iranian desert, you have to understand how Iran arrived at Natanz in the first place. The story of the Iranian nuclear program is not a story that began in the 2000s with the confrontations and ultimatums that most people in the West associate with it. It began decades earlier under a very different government with the active encouragement of the United States, in a period when the word nuclear was associated primarily with progress rather than with danger. In 1957, the United States and Iran signed a civil nuclear cooperation agreement under the Atoms for Peace program, President Dwight Eisenhower's initiative to channel the prestige of nuclear technology into civilian applications and, not incidentally, to bring non-communist nations into alignment with American scientific and industrial interests. Under this arrangement, the U.S. helped Iran obtain its first research reactor, a 5-megawatt facility installed at Tehran University in 1967. Mohammad Reza Shah Pahlavi, Iran's ruler, was fully supportive of nuclear technology. He envisioned a future in which Iran would be a major regional power, and nuclear energy was part of that vision. By the 1970s, the Shah was pursuing an ambitious plan for 20 or more nuclear power plants, and the United States and several European nations were competing for the contracts that would build them. There was a dimension to the Shah's interest that went beyond electricity generation. American intelligence assessments from the early 1970s noted that Iran might be pursuing and might already possess the capability to develop nuclear weapons, and several of the Shah's statements suggested an interest in at least maintaining the option. Henry Kissinger, serving as National Security Advisor and later as Secretary of State under President Richard Nixon, oversaw agreements with Iran that provided substantial nuclear technology transfer, while largely setting aside the question of weapons potential. The Shah was a reliable ally against Soviet influence in the Persian Gulf, and American policy prioritized that strategic relationship over nuclear non-proliferation concerns. This was a choice that would have consequences nobody at the time was fully accounting for. The Islamic Revolution of 1979 changed the equation completely. Ayatollah Ruhollah Khomeini returned from exile in Paris in February of that year, and the government of the Shah collapsed with remarkable speed after months of popular uprising. The revolutionaries who took power viewed the Shah's nuclear program as a symbol of Western dependency and foreign corruption. Several significant contracts were cancelled. The construction of reactors at Bushehr, begun by a German firm, was halted. For much of the early 1980s, nuclear development in Iran was largely dormant, a casualty of the anti-Western ideology of the new government and the enormous financial and human costs of the Iran-Iraq War, which consumed the country from 1980 to 1988 and killed hundreds of thousands of Iranians. But the war itself taught the Islamic Republic something that would prove decisive in shaping its later strategic thinking. When Iraqi forces used chemical weapons against Iranian troops and against Kurdish civilians during the conflict, the international community's response was muted. The United States, which was quietly supporting Saddam Hussein's Iraq during this period as a counterweight to Iranian revolutionary influence, effectively blocked meaningful international condemnation. Iran learned that it stood largely alone in a world where great power politics determined the rules of engagement, and that having no deterrent meant having no protection. This lesson was absorbed at the highest levels of the revolutionary government. It would inform decisions made a decade later when the nuclear program was quietly revived. By the early 1990s, under the leadership of Akbar Hashemi Rafsanjani, Iran had resumed its nuclear pursuits through channels that kept the work out of sight as much as possible. The most consequential of these was the connection to the AQ Khan network. Abdul Qadir Khan was a Pakistani metallurgist who had led Pakistan's uranium enrichment program and who, in the 1980s and 1990s, ran what turned out to be the most dangerous nuclear proliferation network in history. Working through a web of middlemen and suppliers spread across Europe, the Middle East, and Asia, Khan sold centrifuge designs, components, and technical expertise to countries seeking nuclear weapons capability, including Libya, North Korea, and Iran. The centrifuge design he sold was based on European technology that Khan had himself acquired through procurement channels of questionable legality during Pakistan's own weapons development. It was a design known in non-proliferation circles as the P-1, and its derivatives would become the foundation of Iran's enrichment capability, the machines that would be installed in cascades at Natanz, and the machines whose destruction would become the objective of the most sophisticated cyber weapon ever built. Through the 1990s, Iran expanded its nuclear infrastructure with the help of Russian engineers, who resumed work on the Bushehr reactor plant, and through continued clandestine procurement of materials and expertise. The program was declared to the IAEA in partial and carefully managed ways, acknowledging enough to maintain the appearance of compliance with the Nuclear Non-Proliferation Treaty while concealing the full scope of the weapons-relevant work. The Islamic Republic had signed the NPT in 1970, under the Shah, which entitled it to develop civilian nuclear technology, including uranium enrichment, for peaceful purposes, while prohibiting it from developing nuclear weapons. Tehran maintained consistently and publicly that its program fell entirely within the peaceful provisions of the treaty. Much of the world was skeptical. The revelation that shattered this managed ambiguity came from an unexpected source. On August 14, 2002, Alireza Jafarzadeh, a spokesman for the National Council of Resistance of Iran, an exile opposition group, held a press conference in Washington at which he disclosed the existence of two previously unknown nuclear facilities. One was a heavy water production plant at Iraq. The other was a uranium enrichment facility under construction at a place called Natanz, located in Isfahan province on the high, arid plateau of central Iran. Jafarzadeh was specific. He described the facilities' locations, their purposes, and the fact that they had been kept entirely outside Iran's official IAEA declarations. What he described suggested that Iran was building a substantial clandestine enrichment capability that had no plausible civilian justification at the scale being indicated. The IAEA's Director General, Mohammad El-Baradei, pressed Iran for access and eventually obtained it. In February 2003, El-Baradei visited Natanz in person. What he saw shocked him. Beneath the desert floor, a massive underground complex was nearing completion. The above-ground pilot facility had already installed 160 centrifuges and had begun feeding uranium hexafluoride gas into them in experimental operation. The underground halls, designed to hold thousands of centrifuges in large interconnected cascades, were not yet populated with machines, but the infrastructure was clearly being built to accommodate a program far larger than any civilian power generation requirement could justify. El-Baradei's subsequent report to the IAEA Board of Governors confirmed the essential facts and launched years of confrontation between Iran and the international community. Iran's response to the pressure that followed was a mixture of tactical concession and strategic persistence that would characterize its approach for the next decade. Tehran suspended enrichment under a diplomatic agreement with the European powers in 2003 and 2004, but resumed it in 2006 after the talks broke down over the question of permanently abandoning enrichment capability. New UN Security Council resolutions imposed increasingly severe sanctions. The European Union placed restrictions on Iranian banks and oil revenues. The United States maintained and expanded its own extensive sanctions architecture. Iran's economy strained under the cumulative pressure, but the nuclear program continued. What the Islamic Republic's leadership understood, and what its adversaries were only slowly coming to acknowledge, was that Natanz represented something more than simply a technical capability. It had become a matter of national identity, a symbol of sovereignty, of independence, of Iran's insistence that it would not be told by outside powers what technology it was permitted to possess. Supreme Leader Ali Khamenei had issued a religious ruling formally prohibiting nuclear weapons, a fatwa that Iranian officials cited constantly as evidence of their peaceful intentions. Whether that declaration represented a genuine and absolute constraint, or a form of theological positioning that could be revisited if circumstances changed, was precisely the question that kept intelligence analysts awake at night in Washington, Tel Aviv, and European capitals. And at the center of all these calculations, buried under 60 feet of hardened concrete in the desert outside Kashan, the centrifuges spun. By 2007 and 2008, Iran had installed thousands of the machines at Natanz and was steadily accumulating low-enriched uranium. The trajectory was clear, even if the destination remained debated. The world was watching, arguing, and imposing costs. The centrifuges kept spinning. And somewhere in the back rooms of American and Israeli intelligence agencies, people were beginning to think seriously about whether there was a third option between accepting a nuclear Iran and going to war to prevent one. The meeting that changed the course of history did not look like a pivotal moment from the outside. It took place somewhere inside the secure confines of the intelligence and national security apparatus, in a room that had no windows and required multiple layers of credentialing to enter, attended by people whose names would not appear in official accounts for years and whose precise roles remained classified long after the broad outlines of what they decided became public knowledge. What is known, assembled from reporting by journalists who spent years piecing together the story from sources willing to speak carefully and obliquely, is this. Sometime in the middle years of the Bush administration, probably around 2006 or 2007, a serious and sustained conversation began inside American intelligence about whether there was a way to attack Iran's nuclear program that did not involve dropping bombs. The military option had been on the table for years. The Bush administration had made clear that a nuclear-armed Iran was unacceptable, and American military planners had wargamed various scenarios for strikes against Iranian nuclear facilities. The problems with the military option were extensive and well understood. Iran had built Natanz to survive exactly such an attack. The underground halls where the centrifuge cascades operated were buried deep enough and hardened well enough that only the largest bunker-busting munitions in the American arsenal might reach them, and only after multiple penetrating strikes against the same point, a targeting problem that created its own complications. Israel, whose government viewed a nuclear-armed Iran as an existential threat, had been pressuring Washington for permission to carry out its own strike, but Israeli aircraft would have to fly enormous distances over hostile airspace, and even the most optimistic assessments suggested an Israeli strike could at best delay the program by a year or two while cementing Iranian determination to press forward. There was also the question of consequences. A military strike on Iranian nuclear facilities would be an act of war, and Iran had developed a range of responses that could reach far beyond its own borders. Its Hezbollah proxy in Lebanon had tens of thousands of rockets aimed at Israeli cities. Iranian-backed militias operated throughout Iraq, where American forces were still heavily engaged. Iran could close the Strait of Hormuz, through which a significant fraction of the world's oil supply passed, with economic consequences that would ripple through markets everywhere. The Gulf states, which quietly dreaded a nuclear Iran but publicly stood at varying distances from American policy, would be drawn into a regional conflagration whose shape and duration nobody could predict. The military option was not off the table, but everyone who looked at it seriously came away understanding why it was a last resort. Covert action was the space that remained. The CIA had conducted covert influence operations against Iranian nuclear procurement for years, working to disrupt the supply chains through which Iran obtained centrifuge components and other sensitive materials. These operations had achieved modest successes and were considered by most analysts to be a useful but insufficient delaying measure. They slowed things down at the margins. The centrifuges kept coming. Iran's technical community was skilled and persistent, and the black market channels through which it obtained what it needed were resilient and adaptable. The idea that eventually moved from the margins of discussion to the center of serious consideration was something qualitatively different. Not interference with procurement, but direct action against the machines themselves. Not disruption of the supply chain, but destruction of the product. And the method under consideration was not physical. It was digital. The possibility of using malicious software to interfere with industrial control systems had been studied by security researchers and by intelligence agencies for years, but it had never been attempted at scale against a hardened target. The conceptual challenge was immense. To write software capable of navigating from the open internet to the secure interior of an air-gapped industrial facility, finding its way to the specific control systems governing specific machines, and causing those machines to destroy themselves while simultaneously preventing the operators from detecting what was happening required capabilities that pushed the boundaries of what was technically achievable. It also required intelligence access to the target that was extraordinarily detailed, the kind of knowledge that could only be accumulated through years of collection, human sources, and technical penetration. President George W. Bush, according to accounts that emerged years later, was briefed on the program and authorized it. The former president has not confirmed this directly, as the operation remained officially classified for years after his presidency. But multiple credible sources have indicated that the authorization came from the highest levels of the American government, and that it represented a deliberate choice to pursue a new kind of weapon rather than a conventional military response. Within the community working on this problem, the program was given the code name Olympic Games, a designation chosen without any particular irony, as was common practice for intelligence programs. The other essential partner in this endeavor was Israel. The relationship between American and Israeli intelligence agencies in this period was close and multidimensional, involving extensive technical cooperation on many fronts. But the specific concern about Iran's nuclear program gave this cooperation an urgency that went beyond the normal channels of Allied intelligence sharing. Israel's Unit 8200, its signals intelligence and cyberwarfare organization, was by this time among the most capable organizations of its kind in the world. It had developed deep expertise in network penetration, code development, and the exploitation of digital vulnerabilities, built over years of operations in a threat environment that forced continuous innovation. When the Americans brought the Olympic Games concept to their Israeli partners, they found an organization that not only had the technical capacity to contribute substantially but had its own powerful reasons to want the project to succeed. The collaboration that emerged was not without its complications. American and Israeli interests overlapped significantly but were not identical. Israel's timeline pressures were different. Israeli officials believed, with some justification, that the window for effective action was narrower than American planners sometimes acknowledged, because their intelligence assessments of the Iranian program's pace were in some respects more pessimistic. There were debates about targeting parameters, about acceptable levels of collateral effect, about how aggressive the sabotage should be and how quickly it should be deployed. These tensions were managed, as they always are in close intelligence partnerships, through a combination of frank conversation and careful coordination that kept the cooperation functional without papering over the genuine disagreements. What both sides agreed on was the fundamental objective. Iran had constructed, at enormous expense and in the face of sustained international opposition, a centrifuge enrichment program that threatened to change the strategic balance of the Middle East. Diplomacy had not stopped it. Economic pressure was slowing it but not stopping it. Military action was an option of last resort with consequences nobody wanted to manage. The cyberweapon offered a potential fourth path: invisible sabotage that could degrade the program from the inside, set it back by months or years, and potentially do so in ways that left Iran's leaders uncertain about the cause, unable to point to a smoking gun, perhaps even blaming their own engineers for the failures that ensued. This last dimension, the ambiguity, was considered a feature rather than a limitation. An attack that looked like mechanical failure was harder to respond to than an attack that announced itself clearly. It denied Iran the propaganda victory of a visible foreign assault, created doubt and internal friction. It potentially set off cycles of recrimination among the engineers and managers of the program, each group suspecting the others of incompetence or sabotage, when the answer lay outside any of their frames of reference. This was a weapon designed not just to destroy machines but to destabilize the confidence of everyone responsible for maintaining them. The president who inherited the program when he took office in January 2009 had run partly on a platform of diplomatic engagement with Iran. Barack Obama had spoken during his campaign about the importance of direct diplomacy, and his early foreign policy moves included outreach to the Iranian government that reflected this orientation. But Obama was also briefed in detail on Olympic Games almost immediately after taking office, and he not only continued the program but, according to reporting that emerged years later, pushed for it to be escalated. He expanded the operation's scope and authorized more aggressive deployment. The diplomatic and the covert approaches were not mutually exclusive in his administration's thinking. Diplomacy could proceed while the sabotage was running. Perhaps the sabotage would make Iran more willing to negotiate. Perhaps it would simply buy time. Either outcome was preferable to the alternative. What neither Bush nor Obama could know, as they sat through the classified briefings in the secure conference rooms of the White House, was that the weapon their agencies were building would eventually escape the boundaries its creators had designed for it. That it would spread across the world's computer networks in ways that nobody had fully anticipated. That it would be found, publicly identified, and dissected by researchers who would understand almost immediately that what they were looking at represented something new in human history. That the debates and decisions made in those quiet, windowless rooms would eventually become, in outline at least, public knowledge. That their authors would have to account for what they had done in ways none of them had expected. But all of that was ahead. For now, there was a weapon to build, and nobody in the world had ever built anything quite like it. Building a cyberweapon capable of physically destroying industrial machinery is not a task you can assign to a talented programmer and expect results in a few months. The technical requirements are so specific, so deeply layered, and so dependent on precise intelligence about the target that constructing such a weapon is more like an engineering project in the traditional sense than it is like writing software for a consumer application. It requires specialists in computer security, in hardware engineering, in the specific industrial control technologies of the target facility, in nuclear physics, and in the operational tradecraft of covert intelligence, all working in coordination, often in compartmentalized teams who do not fully know what the others are doing, feeding their work into a final product they may never see deployed. The organization on the American side that took primary responsibility for the technical development of what would become known to the world as Stuxnet was the National Security Agency. The NSA is best known as America's Signals Intelligence Service, the organization that intercepts and analyzes communications, that monitors the electronic emissions of foreign governments and military organizations, that reads the data that flows through global communications networks. But the NSA is also, and has been for decades, deeply engaged in offensive cyber operations, the penetration of foreign computer networks for espionage, and, when directed by political authority, for sabotage. Within the NSA, the office most focused on this offensive mission was the Tailored Access Operations Division, known inside the agency simply as TAO. By the mid-2000s, TAO had become one of the most capable offensive cyber organizations in the world, responsible for penetrating networks that ranged from foreign government ministries to military command systems to research institutions. Its operators were among the world's most skilled practitioners of the art of finding vulnerabilities in software and exploiting them before the people responsible for that software had a chance to discover and fix the problems. The Olympic Games project gave TAO a mission unlike any it had undertaken before. Previous operations had focused on espionage. Getting into a network, staying hidden, collecting information, and getting out without being detected. The centrifuge attack required something more intrusive and more difficult to contain. At some point, the code would have to do something visible, something that would damage physical hardware. That moment of action, when the sabotage actually executed, carried risks of detection that pure espionage operations did not, and it required a level of precision about the behavior of the target systems that even experienced NSA operators would need time and specialized knowledge to develop. On the Israeli side, the parallel organization contributing to Olympic Games was Unit 8200, the Signals Intelligence and Cyber Unit of the Israel Defense Forces. Unit 8200 is an interesting organization in several respects. It is large for a military intelligence unit in a country of Israel's size, drawing consistently from among the most technically talented of the young Israelis eligible for military service. Israel's mandatory military service system passes large numbers of technically capable young people through the unit's ranks, creating an unusual relationship between the military cyber apparatus and the civilian technology sector in Israel, where many of the country's most successful technology entrepreneurs and engineers are former Unit 8200 members. By the time Olympic Games was conceived, the unit had accumulated years of experience in offensive cyber operations, including against Iranian targets, and it brought both technical capability and an intimate knowledge of the Israeli threat assessment to the collaboration. From early in the development process, it became clear that successfully attacking the centrifuges at Natanz would require physical as well as digital intelligence. The programmable logic controllers that managed the cascade operations were specific devices running specific software, and attacking them required code that was precisely tailored to their operating parameters. Generic malware that attempted to reach these systems would fail because it would have no way of knowing what to tell the controllers to do, or when to do it. The attack code needed to speak the machine's language fluently, and that required understanding the machines in extraordinary detail. This intelligence-gathering challenge led to one of the more remarkable aspects of the Olympic Games development effort: the construction of a physical replica of portions of the Natanz facility. Working with intelligence about the specific centrifuge models Iran was operating, the specific control hardware being used, and the specific software configurations running on the facility's computers, American and Israeli engineers built what amounted to a test environment in which the attack code could be developed and refined against actual hardware rather than theoretical models. The Idaho National Laboratory, a Department of Energy research facility already involved in nuclear security research, became one site where this testing took place. Researchers there worked with centrifuges similar to those at Natanz, studying the physics of how the machines behaved under the attack scenarios the code was designed to create, verifying that the software instructions would produce the physical effects that were intended. This testing phase was where the project confronted the fundamental challenge of writing code that could cause physical damage without killing its target instantly. The goal was not to blow up the centrifuges in a single obvious event, but to stress them in ways that would cause progressive damage over time, damage that would look like mechanical failure rather than deliberate attack, that would destroy machines gradually enough to be plausibly attributable to normal wear and attrition. The attack needed to be slow enough to create confusion, subtle enough to avoid immediate recognition, but destructive enough to cumulatively degrade the program in meaningful ways. The specific attack mechanism that the development team settled on involved manipulating the operating speeds of the centrifuges in ways that exceeded their design tolerances. The centrifuges at Natanz were designed to operate within a specific range of rotational speeds, governed by the frequency of the electrical signal supplied to their drive motors. The frequency converter drives that controlled this parameter were themselves programmable, and it was through the code running on the programmable logic controllers connected to these drives that the attack would be delivered. What the code would do when it activated was intercept the normal operating commands being sent to the frequency converters and substitute different commands that told the drives to push the centrifuges above their nominal operating speed for periods of time, then drop them sharply below it, then push them high again, cycling through this overspeed and underspeed pattern in ways that the machines had not been designed to sustain. At the same time, the code would be feeding false data back to the operator monitoring screens. The engineers watching their control panels would see readings showing that everything was operating normally. Their instruments, their logs, their alarm systems would all report that the centrifuges were spinning at their correct speeds, that pressures were nominal, that the feed gas flows were within parameters. The machines would be destroying themselves while the monitoring systems calmly reported that nothing was wrong. This was the most insidious element of the design, not just sabotage but deception, ensuring that the victims of the attack would have no basis to understand what was happening until significant damage had already been done. The code was enormous by malware standards of the era, nearly 0.5 megabyte in size, which was extraordinarily large for software designed to spread through networks and avoid detection. The sheer size reflected the complexity of what it had to accomplish. Navigate through multiple layers of operating systems and software environments, install itself without being detected by antivirus tools, assess whether it was in the right type of environment, find the specific industrial control hardware it was looking for, and then execute a precisely choreographed attack sequence. Writing code of this complexity and reliability required time, resources, and talent on a scale that was impossible to conceal entirely, even within the compartmentalized world of classified intelligence programs. The development effort required the equivalent of hundreds of engineer years of specialized work. The teams involved included people who had spent careers studying industrial control systems, people who focused on operating system vulnerabilities, people whose expertise was in antivirus evasion, people who understood nuclear enrichment physics well enough to specify the attack parameters, and people who could think through the operational security dimensions of deploying something this powerful in target systems that might eventually be examined by the world's best security researchers. The possibility that the weapon would someday be discovered and analyzed was not lost on the designers. They built in concealment mechanisms, they designed the code to be difficult to analyze, and they probably operated on the assumption that by the time anyone understood what they were looking at, the damage would be done and the political moment would have passed. What they built, when it was finally complete, was unlike anything that had ever existed in the malware landscape. Security researchers who would later spend months dissecting it would describe it in terms that mixed professional admiration with genuine unease. It was elegant. It was sophisticated. It was the product of a development effort that had clearly been funded and staffed at a level no criminal organization or ordinary hacker group could duplicate. And it was pointed at a specific facility in a specific country with a specific political purpose, making it, in the fullest sense, a weapon of state. Before you can attack a target with any precision, you need to understand it with a depth that most people never have occasion to think about. In conventional military targeting, this knowledge is accumulated through satellite imagery, signals intelligence, human sources, and reconnaissance. You map the defenses, you identify the critical nodes, you study the operating patterns of the people inside, and you build a picture detailed enough to plan an operation that achieves the objective without unnecessary risk or collateral damage. What the Olympic Games team needed to develop for Natanz was a version of this targeting process adapted for an entirely new kind of attack, one that operated not through explosive force but through precise manipulation of digital systems. The Natanz fuel enrichment plant, classified as a nuclear facility under international safeguards and therefore subject to periodic IAEA inspection, was not entirely hidden from public knowledge by the time the Olympic Games development effort began. The broad outlines of its physical layout were known from satellite imagery, which showed the above-ground support structures and the distinctive patterns of construction that marked the buried halls below. IAEA inspection reports, carefully worded but technically specific, provided information about the types of centrifuges being operated, the cascade configurations, the material balance and enrichment levels, and the overall production capacity. This was a better documented target than most covert operations are aimed at, which is one of the strange features of a nuclear program that must make some declarations to international bodies even while concealing others. The facility had two main underground enrichment halls, designated halls A and B, enormous structures buried deep beneath meters of reinforced concrete, each large enough to house dozens of centrifuge cascades in parallel rows. The halls had been sized from the beginning with the intention of eventually housing up to 50,000 centrifuges, a capacity that would give Iran an enrichment rate sufficient for weapons development. By the time Stuxnet was being developed, Iran had installed several thousand machines and was working to commission more. The underground placement of the halls served multiple purposes. It provided protection against conventional military strikes. It maintained the controlled temperature and humidity conditions that centrifuge operations required. And it created a physical separation from the outside world that was reinforced by rigorous security protocols over access, communications, and the movement of people and equipment in and out of the secured zones. The centrifuges themselves were the IR-1 model, Iran's designation for a machine based on the design that AQ Khan had transferred from Pakistan, which was itself derived from European technology. The IR-1 was not a particularly advanced design by international standards. Pakistan had used centrifuges of this lineage decades earlier, and more modern designs that could enrich uranium more efficiently with fewer machines existed in several countries. But the IR-1 was what Iran had in the quantities Iran had, and it was what the attack needed to be designed against. The engineering specifications of the IR-1, its aluminum rotor, its magnetic bearing at the top, its mechanical lower bearing, its specific operating speed range, and the precise rotational frequencies at which it was most vulnerable to structural stress, became essential inputs into the weapon's design. The control architecture of the facility was where the technical attack surface resided. The centrifuge cascades were managed by a distributed control system built around programmable logic controllers, commonly referred to as PLCs, manufactured by the German industrial conglomerate Siemens. Specifically, the facility used two models from Siemens' S7 series, the S7-315 and the S7-417. These were standard industrial automation controllers, widely used in manufacturing plants, power stations, water treatment facilities, and a broad range of other industrial applications around the world. They were reliable, well-documented, and deeply embedded in global industrial infrastructure, which is precisely why Iran was using them. They were not exotic or specially hardened military systems. They were off-the-shelf industrial equipment, the same machines running assembly lines and pumping stations and chemical processes in dozens of countries. The PLCs were programmed and monitored using Siemens Step 7 software, which ran on standard Windows personal computers connected to the control system network. This was where the human interface with the centrifuge cascades resided, the operator workstations, the programming terminals, the historian computers that logged operational data. Understanding precisely how Step 7 worked, how it communicated with the PLCs, what data it stored and how it stored it, and what normal communications traffic between Step 7 and the S7 controllers looked like, was essential for writing code that could insert itself into this communication channel without being detected by routine system monitoring. The frequency converter drives, which translated the PLC's electrical commands into the precise frequencies that governed centrifuge rotation speed, were a particular focus of investigation. The Iranian facility used converters from two manufacturers, a Finnish company called Vacon and an Iranian manufacturer called Ferrero Paya. The Stuxnet code that was ultimately deployed included a specific check for the presence of frequency converter drives operating within a specific speed range, a check so precise that it served effectively as a fingerprint for the Natanz enrichment cascades. If the code did not find frequency converters matching this specific profile, operating within the range of 807 to 1210 Hz, it would not activate its destructive payload. This specificity was deliberate. The weapon was designed to do nothing in the overwhelming majority of computers it might pass through, activating only when it found itself in exactly the environment it had been designed for. This targeting precision required intelligence about the facility that went beyond what IAEA reports and satellite imagery could provide. The codes running on the PLCs, the configuration of the frequency converters, the specific operating parameters of the cascade control loops. This level of detail could only come from sources inside the facility or from extraordinary technical penetration of the procuring organizations. How exactly this intelligence was obtained has never been fully confirmed in open sources, but it is widely believed within the intelligence and security research communities that human sources inside Iran's nuclear supply chain, as well as technical operations targeting companies that provided equipment and software to the program, contributed to the picture. Some researchers have suggested that the IAEA's own inspection data, which included detailed records of the equipment types at Natanz, may have provided useful technical specifications through channels that required no clandestine operation at all. The air gap that the Natanz network operated behind was perhaps the most significant technical challenge in the whole operation, and understanding its precise characteristics was as important as understanding the centrifuges themselves. An air-gapped network is one that has no connection to the public internet and no wireless communications capability. Data moves into and out of it only through physical media, USB drives, CDs, laptops brought in by personnel, specialized data transfer workstations. The people who designed the security architecture of the Natanz facility understood that any connection to the outside world was a potential attack vector, and they had designed the facility to eliminate those connections. An ordinary piece of malware would have no way of reaching the inside of such a network, no matter how sophisticated it was. The delivery mechanism needed to be as clever as the weapon itself. Studying the air gap meant studying the people who crossed it, the engineers, technicians, contractors, and administrators who regularly moved between the outside world and the secured interior. Their workflows, the software they used on machines that also connected to the facility's internal networks, the hardware they carried with them, the software they installed, the procedures they followed when exchanging data with external systems. All of this was part of the targeting picture. The attack code would need to survive in ordinary Windows environments, spread through the types of networks and devices that Natanz-connected personnel routinely used, and eventually find its way across the physical barrier on the back of a USB drive or a contractor's laptop. The development team had to think like engineers doing a security audit of the facility from the outside in. They had to anticipate every pathway by which data legitimately crossed the perimeter and design a delivery mechanism that could exploit those pathways. The time they took to understand the target before writing a single line of attack code was not wasted. When Stuxnet was eventually found and analyzed by the world's security researchers, one of the things that astonished them most was the extraordinary specificity of its targeting. The code knew exactly where it was going and exactly what it was looking for. That precision was the product of intelligence work that predated the coding effort by years. In the world of computer security, a zero-day vulnerability is something that carries a particular weight. The term refers to a flaw in software or hardware that the manufacturer does not know about, for which no patch exists, against which no defense has been built because the people responsible for building the defenses do not yet know the threat is there. The day the manufacturer discovers the vulnerability and releases a fix is the day it becomes a known quantity, the day defenders can begin to close the gap. Before that day, during the 0 days of the vulnerability's existence as an undisclosed secret, anyone who knows about it has a potentially unlimited ability to exploit the affected software. Finding 0-day vulnerabilities in widely used software is a difficult, time-consuming process that requires deep technical knowledge and persistent methodology. Finding for simultaneously usable zero-day vulnerabilities in Microsoft Windows products was something that had no precedent in the malware world. Yet that is exactly what Stuxnet contained when security researchers finally got hold of it and started pulling it apart. For separate Windows zero days, each one a previously unknown flaw that gave an attacker pathways into systems running Microsoft's operating system, all bundled into a single piece of malicious software. Security engineers who worked with Windows vulnerabilities for their entire professional careers would have been fortunate to discover one zero-day in a year of dedicated research. The resources required to develop 4 simultaneously for a single operation represented a level of investment in software vulnerability research that only a well-funded government program could sustain. The 0 days in Stuxnet exploited flaws in how Windows handled print spooler operations, how it processed Windows shell files, how it managed keyboard and mouse driver installations, and how it parsed Windows task scheduler files. Each one, standing alone, would have been a valuable intelligence asset. Using all 4 in a single operation meant spending enormous resources on a single deployment, resources that would be exhausted the moment Microsoft learned of the flaws and patched them. The decision to burn 4 0 days on one operation was itself a statement about how seriously American and Israeli intelligence took the objective. You do not spend irreplaceable capabilities on low-priority targets. The investment implied absolute confidence that destroying the Natanz centrifuges was worth the cost of never being able to use those specific vulnerabilities again. But exploiting Windows vulnerabilities was only one layer of what Stuxnet needed to accomplish. The Windows machines running at and around the Natanz facility were not the actual targets. They were the pathway. The real destination was the Siemens programmable logic controllers at the heart of the Cascade control systems, and reaching those required a second layer of technical sophistication that operated entirely separately from the Windows exploits. Siemens Step 7 software, the programming environment used by engineers to configure and monitor the S7 PLCs, had its own vulnerabilities. Stuxnet exploited flaws in how Step 7 communicated with the physical PLC hardware, inserting itself into the communication layer between the software and the controllers in a way that let it intercept and modify the commands flowing between them. This was essentially a man-in-the-middle attack against an industrial control system, performed with such precision that the software continued to function normally for legitimate users while the malicious code operated beneath it. Engineers using Step 7 to check on their centrifuges would see normal readings. The code that was actually running on the PLCs would have been modified. The history of what the PLCs had been commanded to do would have been altered. The attack existed in the gap between what the monitoring software showed and what was actually happening in the physical machinery. Equally remarkable was the mechanism Stuxnet used to prevent itself from being discovered on the PLC itself. Once the malicious code was installed in the programmable logic controller, it implemented a rootkit at the controller level, hiding its own existence from the Step 7 software that would normally allow an engineer to inspect the PLC's code. If an operator tried to read the controller's programming to verify what was running, the rootkit would intercept that query and return the original, unmodified code, making the system appear clean even to someone who was specifically looking for problems. This was not improvised. It was deliberate and carefully engineered deception built into every layer of the attack. The code-signing certificates used in Stuxnet represented another dimension of its sophistication and another indicator of the resources that had gone into creating it. Digital signatures are a mechanism used by Windows to verify that software has been issued by a known, trusted source. Drivers and other low-level software components are required to carry valid digital signatures before Windows will allow them to run at privileged levels. Stuxnet carried valid digital signatures issued under certificates belonging to 2 legitimate Taiwanese technology companies, Realtek Semiconductor and J-Micron Technology. These were real certificates, not forged ones. They had been stolen from the companies, presumably through operations that involved penetrating the company's internal systems and extracting the private cryptographic keys used to generate the signatures. The use of legitimate stolen certificates meant that Stuxnet could install its driver components on Windows systems without triggering the security warnings that unsigned or questionable software would generate. To Windows, the malicious drivers looked exactly like legitimate software from trusted hardware manufacturers. The fact that certificates from two separate companies were used is itself an interesting detail. It suggests either that the primary certificate was considered to have a limited operational lifespan before the theft would be discovered, requiring a backup, or that different components of Stuxnet used different certificates for different purposes, spreading the risk of detection across the two compromised identities. When both certificates were eventually discovered and revoked by the certificate authorities after Stuxnet's public exposure, it became possible for researchers to trace the timeline of their theft and use, confirming that the operation had been planned and resourced over an extended period. The Stuxnet code was designed in multiple functional components that worked together but which were architecturally separated in ways that reflected the sophisticated thinking of people who had considered carefully what would happen if part of the code were discovered. The spreading mechanism, the installation and persistence routines, the reconnaissance logic that assessed whether the local environment matched the target profile, and the actual attack payload that interfered with the centrifuge control sequences were all distinct components, each one serving its specific purpose in the overall chain from initial infection to ultimate destruction. The attack payload itself was designed with a timing mechanism that introduced another level of operational subtlety. The code did not immediately begin attacking centrifuges the moment it arrived on a new system. Instead, it first performed its assessment, determining whether the PLCs present matched its target profile. If they did, it then waited. The waiting was not random. The attack was programmed to activate intermittently, running for periods of several weeks at a time, then going dormant, then activating again. This cycling behavior served the operational goal of making the centrifuge failures appear to follow the kind of irregular, unpredictable pattern that real mechanical problems display. If every machine had started failing on the same day at the same time, the engineering team would quickly recognize that something systematic was wrong. By spreading the failures across weeks and months, the code created noise in the data that made the true cause harder to identify. There was also a termination condition built into the code. Stuxnet would continue spreading and activating until a defined date, after which it would stop functioning. This kill date mechanism reflected the designer's understanding that the operation was meant to run for a defined campaign period, accomplishing its objectives within a window of time before being shut down. The specific termination date built into some versions of the code provides researchers with a timeline marker that helps establish when those versions were compiled and deployed, contributing to the broader picture of the weapon's development history. The complete weapon, when assembled and reviewed by the dozens of security engineers who later spent months studying it, was described in almost universal terms as extraordinary. Ralph Langner, a German industrial control systems security expert who was one of the first researchers in the world to publicly identify what Stuxnet was targeting, would later say that whoever created it had to be able to look at this from a military perspective. The level of operational sophistication, the careful layering of capabilities, the meticulous attention to avoiding detection, the precision of the targeting. These were the marks of an organization that thought about offensive operations the way military planners think about them, rigorously, systematically, at every level from the strategic objective down to the smallest technical detail. This was not the work of hackers. This was the work of engineers in service of a policy objective, and it showed in every line. There is a particular challenge at the heart of every cyber attack against a well-defended target, and it is a challenge that no amount of technical brilliance can engineer around entirely. That challenge is delivery. You can write the most sophisticated malicious software ever created, code that exploits unknown vulnerabilities, code that hides from every antivirus tool on the market, code that can manipulate industrial machinery with surgical precision, but all of that sophistication is worthless if you cannot get the code into the target system. The Natanz facility had been specifically designed to prevent exactly that. It had no connection to the internet. It had no wireless network that a nearby operator could exploit. Data moved into the facility only through physical means, carried by people who crossed the security perimeter, and those people were subject to rigorous screening and procedural controls designed to prevent unauthorized materials from entering. The air gap was not an oversight. It was a deliberate architectural choice made by people who understood computer security and who had specifically thought about the risk of cyber intrusion. Breaking through it required a delivery mechanism built on patient intelligence work about the humans who crossed the perimeter regularly and the digital tools those humans depended on in their professional lives. The approach Stuxnet used to bridge the air gap centered on USB drives, specifically on the reliable human habit of using portable storage devices to move files between machines in different network environments. USB drives were, and remain, ubiquitous in technical work environments. Engineers and programmers use them constantly to transfer code, to back up work, to carry configuration files between the machine in the lab and the machine in the control room. At a facility like Natanz, where the internal network was segregated from the outside world and email and internet access were controlled, USB drives were one of the primary mechanisms through which software, updates, and data moved across the various security zones. The people who worked there carried USB drives in their pockets and their briefcases, plugged them into machines in multiple environments, and moved them between networks in ways that were routine and unremarkable. Stuxnet exploited this habit through a Windows vulnerability that had been exploited before in simpler contexts but never with this level of sophistication. When a USB drive was plugged into a Windows computer, Windows would normally display an autoplay prompt offering to open the drive or run any autoplay program it found there. Stuxnet used a different mechanism entirely, a flaw in how Windows processed Windows shell link files, which are the shortcut files with the .lnk extension that Windows uses to point to applications and documents. This flaw meant that simply viewing the contents of a USB drive through Windows Explorer, without clicking on anything at all, without accepting any autoplay prompt, was sufficient to trigger the execution of the malicious code. The mere act of inserting the drive and glancing at its contents in the file manager would infect the computer. No user action beyond plugging in the drive was required. This particular infection vector was deeply troubling to security researchers who studied it later because it represented a level of passive exploitation that undermined almost every conventional piece of security guidance about USB safety. Users had been told for years that they should not run programs from USB drives they did not trust. Stuxnet did not ask them to run anything. It infected through the act of viewing. The question of how Stuxnet got onto the initial USB drives that eventually reached Natanz is one that has never been confirmed with complete certainty in public reporting. What seems most likely, based on the analysis done by Symantec and other researchers, was that the initial seeding targeted a small number of Iranian companies with business relationships to the Natanz facility, companies that provided equipment, software, or engineering services to the enrichment program. By infecting computers at these contractor organizations, Stuxnet could get onto USB drives that would eventually be carried inside the facility by contractors or engineers doing legitimate work. 5 Iranian companies were identified as the initial infection points, all of them described by researchers as likely connected to the industrial infrastructure supporting Natanz. From those initial infections, Stuxnet spread through the regular exchange of USB drives and shared network connections in ways that were, in their essential mechanics, mundane. Engineers at a contractor company would work on a project file. A colleague would copy it to a USB drive to take home and review it. That USB drive would go into a home computer. The home computer would be visited by a relative with a laptop. The laptop would go to the office. And so the code spread outward through the ordinary digital traffic of professional and personal life, copying itself to each new drive and each new machine it encountered, but doing nothing visible, causing no noticeable harm, because it had not yet found the environment it was looking for. Stuxnet assessed every new environment it entered carefully and dispassionately. When it arrived on a new computer, it checked a series of conditions. Was the computer running Siemens Step 7 software? Were the right types of Siemens S7 programmable logic controllers connected? Were frequency converter drives matching the target profile present in the connected hardware? If any of these conditions were absent, Stuxnet would continue to spread passively, seeding itself to new USB drives, copying itself to network shares, looking for the next computer, but doing nothing to attract attention and nothing to damage. It was patient in a way that software normally was not, a kind of machine patience that came from having been designed to wait for exactly the right conditions. How long the code waited before finding its way across the air gap into the Natanz network is not precisely known. The best estimates from researchers who analyzed the infection timeline suggest that Stuxnet may have first entered the Natanz control network sometime in 2008 or early 2009, well before the centrifuge failures that would eventually attract serious attention from the engineering staff. The initial entry may have been through a contractor laptop or USB drive, carried through the security perimeter by someone who had no idea they were carrying it, who had connected their drive to an infected machine at their company or at a colleague's home at some point before the work visit and had simply not noticed anything unusual because there was nothing unusual to notice. The image of this delivery is striking in its ordinariness. An engineer or contractor, someone performing entirely legitimate and authorized work at the facility, someone who had passed every security clearance check and every screening procedure that the Iranian nuclear program required of its staff, arriving at the facility with a USB drive in their pocket, signing in at the checkpoint, walking through the corridors, sitting down at a workstation in one of the control areas and plugging in their drive to transfer a configuration file or a project backup. In that moment, without knowing it, without doing anything wrong from their own perspective, they became the delivery mechanism for a weapon that had traveled from government laboratories in the United States and Israel through contractor companies in Iran and into the most secure industrial facility in the country. Stuxnet had crossed the air gap. If you are finding this story as gripping as we do, this is the perfect moment to make sure you never miss another deep dive like this one. Subscribe to the Dead Drop right now, hit the bell so you get notified, and drop a comment telling us where in the world you are watching from. Your support is what makes these investigations possible, and we have many more stories like this one waiting for you. Once inside the Natanz network, Stuxnet began its reconnaissance phase with the same patience it had shown during its long journey to get there. It spread across the internal network through several mechanisms, using shared network drives and Siemens project files to copy itself between machines in the control environment. It checked each new system it reached, cataloging what was present, mapping the network, building up a picture of what was connected to what. And it waited. It waited for the conditions specified in its attack logic to be fully met, for the precise combination of hardware and software that meant, unambiguously, that it had arrived at its intended destination. The attack, when it finally activated, was a masterpiece of sustained deception. Not the loud, immediate destruction of an explosion or a conventional weapon strike, but something quieter and more insidious, operating across weeks and months in the hidden layers of the facility's control infrastructure, doing damage in ways designed to be mistaken for bad luck. The first phase of the attack, after Stuxnet had confirmed that it was connected to the right types of PLCs and frequency converter drives, was recording. For a period of approximately 13 days, the code captured detailed data about normal centrifuge operations. The precise speeds at which the machines ran during their standard working cycle, the normal variations in frequency, the timing of routine status reports. This recording phase gave the attack code a baseline of normal behavior against which it could calibrate the deception it was about to perform. When the false sensor data was later fed back to the operator workstations, it would look like real operational data rather than a static placeholder, because it was based on actual measurements taken from the real machines during their ordinary operation. The attack sequence itself had two principal components that operated in coordinated phases. The first component targeted the speed at which the centrifuges were driven. Under normal operation, the IR-1 centrifuges ran at approximately 1064 Hz, an operating frequency chosen to produce the optimal balance between enrichment performance and mechanical reliability within the specific parameters of that centrifuge model. During the overspeed phase of the attack, Stuxnet sent commands to the frequency converter drives that pushed the centrifuge motors to approximately 1410 Hz, a speed roughly 32% above the design operating point. The machines were not designed to sustain this speed. At 1410 Hz, the aluminum rotors were subjected to centrifugal forces they had not been engineered to handle. Microscopic imbalances in the rotors, which were inconsequential at normal speeds, became significant stresses at elevated rotation. The mechanical bearings that supported the rotors experienced forces outside their design envelope. The gas bearings, which relied on the controlled flow of process gas to maintain rotor alignment, were destabilized by the higher rotational energies. The attack then shifted to its second phase. After driving the centrifuges above their design speed, Stuxnet commanded the frequency converters to drop the operating frequency to a very low value, approximately 2 Hz, for periods of about 50 minutes. This near-stall condition was a different kind of stress. At these extremely low speeds, the gas bearing that supported the bottom of the rotor could not function properly, and the rotor would sag against its lower mechanical bearing in ways that could cause scratching, imbalance, and progressive mechanical damage. The combination of the high-speed stress and the near-stop stress, applied repeatedly over time, created cumulative damage to the rotating components that would eventually cause rotor failure, bearing seizure, or structural fracture of the rotor wall. Throughout all of this, the monitoring systems were receiving false data. The rootkit installed in the PLC firmware was intercepting the actual sensor readings and replacing them with the recorded baseline data from the earlier reconnaissance phase. The operator workstations, displaying what any engineer in the facility would interpret as real-time operational status, were showing centrifuges running at their correct speed, with nominal process readings on every parameter. An engineer looking at his screen would see a cascade operating exactly as designed. The only indicators that something was wrong would be the gradually increasing failure rate of the physical machines. Machines that were dying for reasons that their instruments were incapable of revealing because the instruments themselves had been made to lie. The psychological dimension of this attack on the engineers is worth thinking about carefully. Imagine spending months troubleshooting a problem that your instruments tell you should not exist. The machines are failing at an elevated rate. You examine each one and find structural damage consistent with mechanical stress. But the operating logs show nothing unusual. The control parameters look correct. Every diagnostic tool available to you says that the machines were running normally when they failed. You interrogate your supply chain, looking for substandard components. You review the maintenance procedures, looking for human error. You examine the process parameters, looking for variations in the feed gas that could explain the mechanical damage. Every path leads nowhere. The failures continue. You begin to suspect the instrument technicians who maintain the sensors. You wonder whether someone is falsifying the logs. You question your colleagues. The internal environment of the facility, which depends on trust and professional cooperation for its effective function, begins to corrode under the weight of unexplained failures and the suspicion they breed. Iran has never published detailed accounts of the internal experience of those years. What is known from open sources, from IAEA reports, from analyses by researchers who studied the facility's production data, and from the occasional Iranian official statement that acknowledged difficulties, suggests that the damage was significant. The IAEA's quarterly reports on Iran's declared nuclear activities contain data on the number of centrifuges in operation at Natanz, and this data, when analyzed by researchers like David Albright at the Institute for Science and International Security in Washington, revealed patterns consistent with what the Stuxnet attack was designed to produce. The number of enriching centrifuges declined when, based on the pace of Iran's installation work, it should have been growing. Enrichment output underperformed the theoretical capacity of the installed machines, suggesting that machines were operating below nominal efficiency or that failure rates were consuming capacity faster than commissioning was creating it. One estimate that has circulated extensively, derived primarily from analysis of the IAEA data, is that approximately 1,000 centrifuges were destroyed or severely damaged by the Stuxnet attack. Researchers at various institutions have offered somewhat different numbers, and the precise figure remains uncertain because the Iranian government has never confirmed the details. The program schedule was set back by estimates ranging from 1 to 2 years, which, in the context of a program that had been laboriously built over decades, represented a meaningful delay in the trajectory toward whatever level of enrichment capability Iran ultimately intended to reach. What is equally significant, though less quantifiable, is the operational disruption caused by Iran's inability to understand what was happening. The engineering time consumed by the fruitless investigation of a problem whose cause was invisible to every instrument available consumed resources that would otherwise have been directed toward building and commissioning new capacity. The personnel changes made in response to the unexplained failures, the recriminations and reorganizations and procedural reviews that any organization undertakes when a serious problem remains unsolved despite sustained effort, All of these costs compounded the direct mechanical damage with organizational and human costs that the designers of the attack had understood would flow from their approach. Iran eventually declared, in September 2010, that it had found and removed Stuxnet from its nuclear facilities. By this time, the malware had already been publicly identified outside Iran and was receiving extensive coverage in the international press. The Iranian government attributed the attack to the United States and Israel, though it continued to insist that the damage had been limited and the program essentially unaffected. These claims were generally viewed skeptically by Western analysts who had studied the production data, but they served a domestic political purpose, asserting that the Islamic Republic's program was resilient and that its enemies had failed. The reality, as best as it can be reconstructed from available evidence, was considerably more painful for the engineers who had spent years building what those centrifuges were supposed to accomplish. Minsk, the capital of Belarus, is not a city that appears often in the history of Cold War espionage or nuclear geopolitics. It sits on the flat plains of Eastern Europe, a city of broad Soviet-era boulevards and functional architecture, rebuilt almost entirely after the Second World War destroyed it, home to a population that has lived through more than its share of the 20th century's upheavals. In 2010, it was the headquarters of Virus Blockade, a small antivirus company with a limited international profile, staffed by security engineers whose daily work involved examining malicious software, adding signatures to detection databases, and responding to customer reports of unusual behavior on their computers. On June 17, 2010, Virus Blockade received a complaint from a customer in Iran. The customer's computer was behaving strangely, repeatedly crashing and rebooting in a pattern that suggested something seriously wrong with either the hardware or the installed software. This was not an unusual type of complaint for an antivirus company. The security engineers assigned to investigate began with the standard diagnostic approach, collecting information about the system environment, examining what software was installed, looking for obvious signs of known malware. What they found instead was something that none of their signature databases recognized, a piece of code that behaved in ways none of them had seen before, that used techniques that were novel and that appeared, as they looked more closely, to be extraordinarily sophisticated. The engineer who first identified the anomalous code was Sergey Ulysin, a malware researcher at the company with years of experience examining adversarial software. His initial analysis identified the LNK file exploit, the Windows shortcut vulnerability that Stuxnet used as one of its primary spreading mechanisms. This was a previously unknown attack technique, and Ulysin recognized immediately that he was looking at something out of the ordinary. In mid-July 2010, Virus Blockade published a security advisory describing the LNK vulnerability and including enough technical detail that other security researchers could begin their own investigations. That advisory was the stone dropped into still water whose ripples would circle outward for years. Within days of its publication, security researchers at major antivirus and security companies around the world had picked up the thread and begun pulling. Microsoft issued an emergency advisory acknowledging the LNK vulnerability and recommending that users disable the Windows Shell autoplay feature as a temporary mitigation. The antivirus community began collecting samples of the malware and submitting them to shared analysis databases. Within weeks, what had started as a complaint from an Iranian customer to a Belarusian antivirus company had become the subject of intensive investigation by security teams at organizations including Symantec, Kaspersky Lab, F-Secure, ESET, and a dozen others. But the discovery's significance went beyond the specific technical puzzle it presented. As researchers began to map the infections reported to their systems, a geographic pattern emerged that was immediately striking. The vast majority of computers infected with this malware were in Iran. The exact proportions varied depending on the measurement methodology and the time frame of the data, but consistent with multiple analyses, somewhere between 58 and 65% of all observed Stuxnet infections were in Iranian machines. Indonesia was second, with India third. Several other countries showed smaller numbers of infections. But the concentration in Iran was so dramatically disproportionate that it immediately eliminated any interpretation of the malware as generic criminal software designed to steal credit cards or harvest banking credentials. Criminal malware follows the money, and the money was in the developed world, not in Iran. This malware was strikingly concentrated in a country that international security services had been watching with intense interest for years because of its nuclear program. The geographic distribution, combined with the technical sophistication of the code that was now being studied intensively by researchers around the world, began to generate speculation that was remarkable for the normally restrained world of computer security analysis. By late July and early August of 2010, security researchers were writing publicly that the malware's characteristics suggested a nation-state origin, that no criminal group or hacktivist collective had the resources or the motivation to build something this complex, and that the concentration of infections in Iran pointed toward a specific political objective. Iran's Computer Emergency Response Team, known as MAR, acknowledged in late September 2010 that its systems had been infected with Stuxnet and that they had identified and removed the malware from affected machines. The official statement described the network of infections in Iran as numbering around 30,000 industrial computers, though this figure was drawn into question by independent researchers who believed the total might have been higher. Iranian officials characterized the incident as an act of cyber warfare and attributed it to foreign adversaries, though at this stage the attribution was not publicly specific to any named government. What Iran's official statements did not address, or could not address because the extent was not yet visible even to them, was that Stuxnet had spread considerably further than the Natanz facility and the industrial companies in its immediate supply chain. The USB spreading mechanism and the network propagation capabilities had carried the code into an enormous range of computer systems in Iran, most of which had nothing to do with the nuclear program. Ordinary businesses, government offices, universities, and private individuals had all been infected, their computers silently carrying code that was doing nothing at all to them because they lacked the specific industrial hardware the attack required to activate. But the code was there, and it was spreading, looking for its target in the same patient, systematic way it had been designed to search. Outside Iran, infections were appearing in a widening arc of countries that extended well beyond any plausible set of nuclear program contractors. Indonesia, India, Pakistan, Kazakhstan, the United Kingdom, Australia, Germany, France. Stuxnet had spread through the ordinary traffic of USB drives and shared network connections across a growing number of the world's computer systems. Most of these infections were dormant by design, code that would check its environment, find no Siemens PLCs of the right type, and simply remain passive, spreading to the next USB drive it could reach, waiting for conditions that almost certainly would never be met on the vast majority of computers it visited. But the spreading was real, and it was global, and it was the first indication that the designers of the weapon had not fully controlled what happened after deployment. A second version of Stuxnet, one that researchers later dated to 2010, contained a change in the spreading mechanism that was more aggressive than the version deployed in 2009. Where the earlier version had included a check that prevented a single copy of the code from spreading to more than 3 machines from a single originating USB drive, the 2010 version relaxed this constraint in ways that allowed more widespread propagation. This change, it was later reported, was the modification that caused Stuxnet to escape beyond its intended operational boundaries and spread onto the global internet in ways that the program's designers had not authorized and, reportedly, had not anticipated. The question of who made that change and why, whether it was an authorized modification or an error in the development process, has never been definitively answered in public reporting. What is clear is that by the summer of 2010, the weapon was out in the world. It was being found and analyzed by researchers who understood neither its full purpose nor its origin. The story of the centrifuges, the story of what had been happening underground in the Iranian desert for the past year or more, was about to move from the classified world where it had lived entirely into the open, where anyone with the technical skills to assemble the evidence could begin to read it. The security research community that assembled around Stuxnet in the summer and early autumn of 2010 was a loose, distributed, and largely self-organizing network of people spread across several countries and organizations, brought together not by any institutional mandate but by professional fascination with an object that none of them had ever seen anything like before. The culture of this community had been built over decades of collaborative analysis, a tradition of sharing samples and findings through mailing lists, conferences, and informal networks that connected researchers at competing companies who nonetheless cooperated on technical analysis because the work was interesting and because a rising tide of understanding lifted everyone in the field. Stuxnet tested and ultimately validated that tradition in ways that nobody had anticipated. At Symantec, the American cybersecurity company headquartered in Cupertino, California, two researchers named Liam Omerchu and Eric Chien took the early lead in what became one of the most intensive and consequential reverse engineering efforts in the history of computer security. Omerchu, an Irish-born analyst with a background in malware analysis spanning years of work at Symantec's security response team, received the first Stuxnet samples in July 2010 following the disclosure of the LNK vulnerability by Virus Blockada. He began the analysis that would occupy him and his colleagues essentially full-time for the next several months, producing a series of technical papers that steadily expanded the security community's understanding of what Stuxnet was. The process of reverse engineering a sophisticated piece of malware is not glamorous work. It involves taking executable code, binary numbers that represent machine instructions, and working backward from those instructions to understand what the code is designed to do. Most modern malware is also obfuscated, meaning it uses techniques designed to make this analysis more difficult, encrypting parts of its code using multiple layers of compression, employing anti-analysis tricks that detect when the code is being run in an analysis environment and behave differently as a result. Stuxnet used all of these techniques, and it used them well. The code had been compiled from a very large codebase by people who anticipated that it would eventually be captured and analyzed. The analysis effort required constant creativity, patience, and the willingness to spend days or weeks on a single function or module before breaking through to understand what it was doing. What Omerchu, Chien, and eventually dozens of other researchers around the world found as they worked through the code was astonishing at every level. The sheer size of the code was the first thing that struck any researcher who received a sample. Stuxnet was approximately 500 kilobytes in size, roughly equivalent to a long text document in storage terms, but enormous for malware, which is typically designed to be as small as possible to aid in spreading and to minimize its footprint on infected systems. Something worth half a megabyte had been packed into this executable. That scale implied a level of functional complexity far beyond anything the security community had encountered in criminal malware. As the researchers dug deeper, the layers of sophistication kept revealing themselves. The 4 zero-day Windows vulnerabilities were identified and reported to Microsoft, which issued emergency patches. The 2 stolen code signing certificates from Realtek and Jmicron were identified and reported to the certificate authorities, which revoked them. The spreading mechanisms were mapped and documented. And with each layer that was understood, new and stranger layers appeared beneath it. The discovery of the PLC targeting components was the moment when the analysis shifted from technically remarkable to historically significant. Most of the researchers analyzing Stuxnet had backgrounds in Windows malware, in viruses and trojans and rootkits that attacked operating systems and applications, stole data, and maintained persistence on compromised machines. The Siemens Step 7 and PLC components of Stuxnet were in territory that almost none of them had ever worked in before. These were not Windows programs. They were code designed to run on specialized industrial hardware operating under proprietary Siemens software, code that spoke a completely different technical language from the rest of the malware ecosystem. The researchers who were grappling with the Windows-side components found themselves staring at code blocks that their tools could not automatically analyze and that their professional training provided no framework to interpret. The industrial control systems security community, a small and specialized subset of the broader cybersecurity world, was brought into the analysis by necessity. Researchers who spent their careers studying the security of power plants and manufacturing facilities and water treatment systems suddenly found themselves at the center of an investigation that the entire security world was watching. They could read the Siemens code. They understood what a programmable logic controller was and how it communicated with its supervisory software. And what they found when they applied their expertise to the Stuxnet PLC components was genuinely alarming. The code was designed to intercept communications between Step 7 and specific models of Siemens S7 controller. It was designed to inject its own commands into those communications to modify the behavior of the controllers it infected. It was designed to hide its modifications from the software that engineers would use to inspect the controllers. And it was specifically tuned to the operating parameters of centrifuge drive systems, the frequency ranges, the timing cycles, the speed profiles. All of this was there in the code, visible to anyone who had the expertise to read it and the time to work through the obfuscation layers. The weapon's objective was embedded in its code, waiting to be read by anyone who knew the language. In Hamburg, Germany, a security engineer named Ralph Langner was working through the Stuxnet materials independently, supported by a small team at his industrial control systems security consultancy. Langner had spent his career in the highly specialized world of control system security, helping industrial operators understand and mitigate the cybersecurity risks to their physical plant equipment. When Stuxnet came to his attention, he recognized immediately that the PLC targeting components represented something he had never seen before, a direct attack on the digital logic controlling physical machinery. By late September 2010, Langner had done enough of his own analysis to reach a conclusion that he was willing to state publicly. Stuxnet was designed to attack a specific industrial process, and based on the technical characteristics of what it was targeting, he believed that process was uranium enrichment centrifuges, and that the target was in Iran. Langner published his analysis on his website on September 25, 2010. It was a moment of remarkable public clarity. Other researchers had been cautiously circling the same conclusion, but Langner stated it directly and specifically, with supporting technical argumentation. The centrifuges. Iran. A cyber weapon designed to destroy physical infrastructure. He went further, stating publicly that the sophistication of the code required state-level resources and that the most likely originating states were the United States and Israel. He acknowledged he was speculating on the attribution, but he was not speculating on the technical conclusion about the target. That was in the code. The security world reacted to Langner's publication with a mixture of validation and careful restatement by organizations that felt the public statements warranted more caution than Langner had applied. But the cat was out of the bag. The mainstream technology press picked up the story. The New York Times, the Washington Post, and major media organizations around the world ran pieces about the discovery of a cyber weapon apparently aimed at Iran's nuclear program. The phrase that appeared in story after story, drawn from the technical analysis and translated for general audiences, was that this was the first known cyber weapon designed to cause physical destruction. That description, in its directness and precision, captured exactly what made Stuxnet different from everything that had come before it in the history of computer security. The full technical picture of what Stuxnet did took months to emerge in the open literature, built up through the cumulative work of dozens of researchers publishing and communicating through the informal networks of the security world. Symantec's formal detailed analysis, published in September 2010 under the title Stuxnet Under the Microscope, ran to more than 60 pages of technical documentation. It was updated and revised multiple times as new findings emerged. No previous malware analysis document in the history of the industry had come close to matching its length or the depth of its technical documentation, and it would be supplemented by equally substantial work from Kaspersky Lab, F-Secure, ESET, and individual researchers publishing through conference presentations and personal publications. What the assembled analysis eventually confirmed went beyond what any of the initial reporting had fully captured. The precision of the targeting, once the industrial control system components were fully analyzed, was extraordinary in its specificity. The code contained hard-coded configuration values that checked for frequency converter drives from two specific manufacturers, Vacon of Finland and Ferrero Paya of Iran, operating at specific frequency ranges. These were not generic industrial conditions. They were the fingerprint of a specific class of enrichment equipment at a specific type of facility, and the code would sit dormant on any computer system that did not match this precise profile. The researchers discovered that Stuxnet tracked the number of Siemens control units it found that matched its target criteria. It required at least a minimum number of matching controllers before activating its full attack payload, another precision technique ensuring that it was operating in a large-scale industrial environment rather than in a single machine test setup. The attack would not activate against one or two controllers. It was designed for the conditions of a large centrifuge cascade hall, where many controllers were connected together in the networked configuration used at Natanz. The details of the attack sequence itself, as fully documented through the analysis, were even more specific than early reports had indicated. The code did not simply run the centrifuges fast and then slow. The timing of the attack phases, the duration of the overspeed and underspeed cycles, the intervals between activation periods, all of these parameters were carefully chosen to align with the mechanical characteristics of the specific centrifuge model being targeted. The researchers who reconstructed the attack sequence by working through the control logic concluded that someone had done detailed engineering analysis of the IR-1 centrifuge's vulnerability to speed variation, identifying the specific frequency ranges and timing that would create the maximum cumulative stress on the rotor structure without triggering any single catastrophic failure that would have been immediately obvious. The deception layer was what many researchers found most disturbing. The rootkit that concealed the attack from operator monitoring was not a crude mechanism. It had been built with detailed knowledge of how Siemens diagnostic software queried the PLC firmware, and it responded to those queries with data that was technically correct in its format and plausible in its content but fundamentally false in its representation of what the machines were doing. The engineers running those diagnostic checks were not victims of casual deception. They were victims of precisely calibrated technical fraud, designed by people who had studied the monitoring tools as carefully as they had studied the machines being attacked. There was a human dimension to all of this that the dry technical analysis papers could not entirely capture. The researchers who worked through the Stuxnet code were themselves people who spent their professional lives building defenses, studying attacks for the purpose of building better protections, and maintaining a professional orientation towards cybersecurity as a fundamentally defensive activity. What they were looking at was a weapon, built for offensive use by a government, used in ways that caused real physical damage. This was not what any of them had expected to spend their careers analyzing. Several of the researchers who spoke publicly in the months after the discovery described their feelings in terms that acknowledged the historical weight of the moment. Eric Chien of Symantec would later describe the analysis as the most technically challenging work he had done in his career, but also as something that carried implications beyond purely technical interest. Liam O'Murchu gave presentations at security conferences where the audience, deep technically and normally reserved in its professional judgments, responded with an unusual mixture of intellectual excitement and what could fairly be described as alarm. They understood, in a way that the general public was only beginning to grasp, what the deployment of something like this against industrial infrastructure meant. For the broader public, the Stuxnet story broke into mainstream consciousness in the autumn of 2010 through reporting that translated the technical findings into terms that non-specialists could understand. The Iranian nuclear program was already a topic of intense public and political interest. The idea that it had been physically disrupted by a piece of software, by code written in laboratories and delivered through ordinary USB drives, by a weapon that operated entirely in the digital domain but produced real physical destruction, was genuinely new. It required people to update their mental model of what was possible in the world of conflict, to add a new category to their understanding of how nations could act against one another. The IAEA, which maintained its regular inspection visits to Natanz through this period, had its own perspective on the events that the technical analysis was revealing. The agency's inspectors had observed the declining number of operational centrifuges and the underperforming production statistics over the 2009 to 2010 period and had documented them accurately in their public reports, without being able to explain them. The Stuxnet revelations provided the explanation the inspectors' data had been missing. Later reconstructions of the IAEA data against the timeline of the Stuxnet attack showed a correlation that was hard to interpret as coincidental. The declines in centrifuge numbers, the periods of particularly poor production performance, tracked closely with what was now understood about the timing of the attack's active phases. Iran's nuclear program had been set back. By how much and for how long was a question that analysts would debate for years. The academic and policy research institutions that track Iran's nuclear program closely published competing assessments of the delay, most ranging from 1 year to 2 years, with the wide range reflecting the difficulty of separating the effects of Stuxnet from the effects of other factors. the procurement difficulties caused by sanctions, the ongoing challenges of operating centrifuges that were not optimally designed, the management and personnel issues that affected any large industrial program over time. But the direction of the effect was not in serious dispute. Stuxnet had caused real damage, and it had done so invisibly, in ways that Iran's engineers could not defend against because they could not see what was attacking them. The revelation that created the most lasting unease was not about what had already happened, but about what it implied for the future. Cyber weapons that could physically destroy industrial infrastructure were no longer theoretical. They had been built. They had been deployed. They had worked. The question of who might build such weapons next, and against what targets, was now a practical question rather than a speculative one. And the answer that most analysts reached, surveying the global landscape of industrial infrastructure and the proliferation of programmable control systems that now governed everything from power grids to chemical plants to hospitals to transportation networks, was not a reassuring one. One of the persistent challenges in the world of covert operations is that attribution, the identification of who is responsible for an action, is simultaneously very important and very difficult to establish with certainty. States that conduct covert operations rely on deniability as a structural feature of the enterprise. The operation is designed and executed in ways that allow the sponsoring government to deny involvement, to maintain plausible ambiguity, to avoid the full diplomatic and political consequences that would attach to openly acknowledged action. Cyber operations were long considered to offer particularly strong deniability because the technical evidence could be manipulated, because the distance between the computer that delivered an attack and the human beings who designed it was invisibly large, because code left no fingerprints in the conventional sense. Stuxnet challenged this assumption in a fundamental way. The very sophistication of the code that made it effective as a weapon also made it distinctive as an artifact. The resources required to build it, the specific intelligence about the target embedded in its design, the operational context in which it had been deployed, all of these factors combined to create a body of circumstantial evidence that pointed with considerable force toward a small number of possible authors. The security researchers who studied the code were not intelligence analysts, and they did not claim to have the classified information that would definitively establish attribution. But they could read what was in front of them, and what they read told a story. The technical indicators were numerous. The code was written with an engineering quality and attention to anti-analysis techniques that reflected professional software development practices at a high level, the kind of development environment with extensive testing and quality assurance processes that government programs have and criminal organizations generally do not. The use of 4 zero-day Windows vulnerabilities simultaneously, the investment in stolen code signing certificates, the testing of the attack against physical centrifuge hardware. None of these were within the reach of any private actor with the motivations that would explain targeting Iran's nuclear program. Only a government or a very small number of extremely well-resourced governments could have assembled the capability. The list of governments with both the technical capability and the strategic motivation to attack Iran's uranium enrichment program was short. The United States' motivation required no elaboration. Iran's nuclear program was the central proliferation concern in American foreign policy. The United States had the world's most capable signals intelligence and cyber operations organization in the NSA. It had the industrial and scientific research infrastructure to build and test the centrifuge attack components. It had the intelligence collection capability against Iran that would provide the targeting information the code required. Every line of the intelligence and capability checklist pointed to the United States as the most probable author. Israel's position on the list was almost as strong. Israel had been more publicly and urgently vocal about the existential threat it perceived from an Iranian nuclear weapons capability. Its Unit 8200 had been identified by researchers and former officials as one of the world's premier offensive cyber organizations. The specific technical characteristics of some components of the Stuxnet code showed similarities to other Israeli cyber operations that security researchers identified in subsequent years, though these connections were never definitively established in public reporting. And Israel's intelligence service, the Mossad, had been conducting a parallel campaign of what officials and journalists described as physical sabotage against Iran's nuclear program, including the assassination of several Iranian nuclear scientists over a period of years that overlapped with the Stuxnet deployment. This pattern of behavior was consistent with a government that had decided to act against the program across multiple methodologies simultaneously. Some researchers found a potential cultural clue in a string within the code. The Stuxnet files contained a reference to the word murtis, which researchers speculated might be a reference to the Book of Esther from the Hebrew Bible. Esther, whose Hebrew name was Hadassah, is the book that tells the story of Persian Jews who were threatened with destruction and who struck preemptively against the threat. The narrative parallel to Israel preemptively striking against a Persian threat in the nuclear age was not lost on the researchers who noticed it. The connection was widely reported, though it was also widely cautioned as speculative and possibly a coincidence or an attempt to plant misleading evidence. The number 197900509, found in the code as a hard-coded date value in a format corresponding to May 9, 1979, was another potential cultural indicator. That date has been linked to the execution of Habib el-Ghanian, a prominent Iranian Jewish businessman who was the first Jewish Iranian executed after the Islamic Revolution, an event that prompted a mass emigration of the Iranian Jewish community. Whether this number represented an intentional symbolic reference or had another technical explanation was debated by researchers without resolution. The path from technical analysis to official attribution took years and traveled through journalism. David Sanger, the chief Washington correspondent of the New York Times, had been working his sources in the American national security establishment for months on the Stuxnet story. His reporting, which appeared first in a major Times article in January 2011 and was later expanded in his 2012 book Confront and Conceal, drew on conversations with current and former officials who spoke carefully in ways that confirmed, without formally acknowledging, the broad outline of what researchers had concluded from the technical evidence. The United States and Israel had built and deployed Stuxnet. The program had been authorized at the presidential level under Bush and expanded under Obama. The code name was Olympic Games. The objective was to delay Iran's nuclear program and create an alternative to military action. Sanger's reporting triggered an official classified investigation into the leak of classified information, one of several such leak investigations pursued by the Obama administration. The investigation, which involved the FBI and the Justice Department, never produced criminal charges against any government official. Sanger himself was not prosecuted, as the First Amendment protections for journalists receiving leaked national security information provided political and legal obstacles that the administration ultimately did not pursue. The confirmation that many observers had treated as implicit in various official statements and non-denials came in a form that was technically indirect but practically unambiguous. When President Obama was pressed on Stuxnet during the 2012 presidential campaign, he declined to confirm or deny the specific program, as was standard practice for classified operations. But his administration did not dispute the core reporting, and former officials who spoke on background were consistently confirming the essentials to journalists who pressed carefully enough. The world intelligence community, if not the general public, had arrived at a settled view about who had built the weapon, even in the absence of a formal government acknowledgement. That acknowledgement would come, in oblique form, from an unexpected direction years later when documents provided by former NSA contractor Edward Snowden to journalists in 2013 included references to a joint NSA and GCHQ program that involved technical operations against Iran's nuclear program. The documents did not explicitly name Stuxnet or Olympic Games, but the context left little room for any interpretation other than confirmation that American and British intelligence had been involved in cyber operations targeting Natanz. Combined with the reporting on the American-Israeli collaboration, the picture was essentially complete even without the formal government statement that standard diplomatic practice would never provide. The full reckoning with what had been authorized and deployed in those underground halls, a reckoning that governments conduct internally but that democracies eventually must grapple with publicly, remained unfinished business for years after the weapon's disclosure. Who authorizes a cyber weapon? What oversight governs its use? What accountability follows if it causes damage beyond its intended target? These questions, raised implicitly by the Stuxnet episode, had no satisfactory answers in 2010, and the absence of those answers would matter considerably in the years to come. The designers of Stuxnet had built containment into their weapon from the beginning. They understood, or should have understood, that releasing malicious code into the wild carried risks that went beyond the intended target. An operation designed to degrade a specific facility in a specific country, operating against specific hardware in a specific configuration, could not be allowed to become a general disruption to the global industrial infrastructure that used similar control systems. The Siemens PLCs that Stuxnet was targeting were not unique to the Natanz enrichment program. They were used in water treatment plants, in manufacturing facilities, in power generation, in chemical processing operations around the world. If Stuxnet activated indiscriminately across all the environments it spread into, the resulting damage could extend far beyond the intended target and create consequences that even the program's most aggressive proponents would not have sanctioned. The primary containment mechanism the designers built was the targeting precision itself. The code's requirement for frequency converter drives from specific manufacturers, running at specific frequency ranges, in configurations that included minimum numbers of matching controllers, was an extremely narrow fingerprint that the vast majority of Siemens control installations in the world would not match. A water treatment plant with Siemens controllers would not have those frequency converters operating at those speeds. A manufacturing plant automating an assembly line would not match the centrifuge cascade profile. The targeting specificity served simultaneously as the operational accuracy requirement and as the containment mechanism. A second containment mechanism was a limit on how many times a copy of the code could spread from a single USB drive. The design intention was that any given infected USB drive would spread to no more than 3 other computers, preventing unlimited exponential propagation from a single point of infection. In combination with the dormancy of the code on systems that did not match the target profile, these mechanisms were intended to keep the operational spread of Stuxnet within bounds that the program's designers considered manageable. Enough spread to reach the target facility through the supply chain vectors, but not so much spread that it would become a globally disruptive phenomenon. These containment mechanisms worked reasonably well for the version of Stuxnet that researchers later dated to 2009. Then something changed. The 2010 version of Stuxnet, compiled and deployed by the teams who continued developing the weapon as the operation proceeded, made changes to the spreading behavior that relaxed the containment constraints. Exactly what changes were made, and why, is something that has been analyzed from the outside by researchers who could examine the compiled code but could not read the planning documents that might explain the decision. What the code itself shows is that the 2010 version spread more aggressively. The 3-machine limit from USB drives was modified. The dormancy of the code on non-target systems continued, but the mechanics of propagation had changed in ways that allowed wider distribution. According to reporting that attributed the information to senior American officials, President Obama was informed when he received his regular intelligence briefings that Stuxnet had escaped. The specific nature of that escape, the wider spread that the 2010 version was producing, apparently came to his attention at a moment when the Olympic Games operation was approaching a decision point. Obama reportedly had the option to pull the plug on the operation, to shut it down before additional deployments, based on the concern that the weapon was no longer contained within the boundaries its designers had specified. He reportedly chose to continue. The rationale for continuing despite the containment breach apparently rested on the assessment that the damage to the Natanz program was significant and ongoing, that the centrifuge failures were producing real delays in Iran's enrichment capacity, and that stopping the operation at that point would sacrifice those gains for a containment problem that had not yet produced visible harmful consequences outside Iran. The code was spreading, but it remained dormant on the vast majority of systems it reached. The probability of it activating inappropriately on non-target industrial systems was considered low, if not zero. The security researchers who analyzed Stuxnet comprehensively in the autumn of 2010 had a different perspective on this calculation. They had mapped a global infection that extended to hundreds of thousands of computers in dozens of countries. The vast majority of those infections were on ordinary business and consumer computers where Stuxnet was inert, unable to find the industrial hardware it needed to activate. But the distribution of Siemens control systems in the world was broader than the infection models may have anticipated. Several security researchers expressed publicly what they considered to be a real, if low probability, risk that Stuxnet might reach industrial control environments outside the enrichment context where the frequency converter configurations happen to be close enough to the target parameters to trigger some portion of the attack behavior. The concern was not that Stuxnet would strike a power plant or a chemical facility and cause catastrophic damage. The concern was that nobody could be certain exactly where the boundaries of the targeting fingerprint fell, and that the people responsible for the weapon were no longer in a position to recall or disable it. This was the fundamental nature of the problem that Stuxnet had created, a problem that would define discussions of cyberweapons policy for years afterward. A weapon released into the digital environment could not be recalled in the way a military unit could be ordered to stand down. It could not be detonated safely in the way an unexploded bomb could be rendered inert by demolition specialists. It would continue propagating as long as there were USB drives to carry it and network connections to spread across. The kill date mechanisms that had been built into the code would eventually cause deployed copies to stop functioning, but not before the code had been copied, studied, and potentially repurposed by researchers or intelligence services who obtained it. The version of the code that Virus Blockade found in June 2010, the version that the global security community then analyzed intensively through the rest of the year, was now available to anyone who wanted to examine it. The source code had not been published and was not available, but the compiled executables were in the hands of thousands of researchers worldwide, in shared malware databases, in the analysis sandboxes of every major antivirus company. Any capable reverse engineer could work through the functionality that Liam Omerchu and Ralph Langner and dozens of others had documented publicly. The weapon had been disclosed as surely as if its blueprints had been posted online. Governments and security researchers worried about what this disclosure meant for future adversaries. A poorly resourced state or a non-state actor studying the Stuxnet analysis papers would learn not just what the weapon did, but how the development approach worked. They would learn the value of zero-day exploits. They would learn how to reach air-gapped networks through supply chain attacks. They would learn what a PLC targeting rootkit looked like and begin thinking about how to build equivalent capabilities against different industrial targets. The disclosure did not immediately enable copycat attacks, because the technical capability required to build something of Stuxnet's sophistication remained beyond most actors. But it moved the frontier of demonstrated possibility, and it provided a detailed template that would inform the next generation of development in offensive cyber capabilities worldwide. The debate within the American national security community about whether the operation had been worth the cost of its disclosure was vigorous and, by nature of the subject matter, conducted entirely out of public view. What was visible were the policy adaptations that followed. Expanded efforts to secure industrial control systems, new attention to supply chain security for critical infrastructure, joint public-private initiatives to improve the security of Siemens and other industrial control platforms, and a gradually intensifying focus within government cybersecurity programs on the protection of physical infrastructure from digital attack. These adaptations acknowledged, implicitly but unmistakably, that the government agencies responsible for national security had understood the implications of what they had shown was possible. Iran's initial response to the Stuxnet affair followed the pattern that any government in a comparable position might have adopted. Publicly minimized the damage, attributed the attack to external enemies, and denied that the nuclear program had been meaningfully impaired. These statements served domestic political purposes in a country where the nuclear program had become a symbol of national sovereignty and technical achievement, and where acknowledging that foreigners had successfully infiltrated the most sensitive industrial facility in the country would have carried considerable political embarrassment. The official posture of resilience and defiance was maintained even as the engineering staff at Natanz worked through what the IAEA's inspection records had confirmed was a significant reduction in operational centrifuges. What was less visible at the time, and only became clear through events that unfolded over the following years, was that Iran drew a set of strategic lessons from the Stuxnet episode that would make it a considerably more capable and more dangerous actor in the domain of offensive cyber operations. The attack had demonstrated something important to the Islamic Republic's leadership, that the digital sphere was not merely a domain in which Western powers held advantages, but a domain in which smaller and less wealthy states could inflict meaningful costs on adversaries at a fraction of the investment required for conventional military power. The logic was the same logic that had driven the development of the AQ centrifuge design in the first place, the logic of asymmetric capability, using specialized technical investment to reach for effects that conventional military balance would not permit. By 2011 and into 2012, Iran had made substantial investments in building its own cyber warfare capabilities. The specific organizational structure of the Iranian cyber program is not fully documented in open sources, but researchers who track Iran's digital activities, particularly at the Clavis Technology Institute and organizations like Mandiant and CrowdStrike, documented a rapid maturation of Iranian offensive cyber capability in the years following Stuxnet. The Islamic Revolutionary Guard Corps established units dedicated to offensive cyber operations that were reportedly operating with increasing sophistication and audacity by 2012, drawing on both talent recruited from the country's considerable computer science and engineering community and knowledge gleaned from analyzing the cyber operations conducted against Iran's own systems. The attack that most dramatically announced Iran's new offensive posture came in August 2012. On the 15th of August of that year, a piece of malware known as Shamoon began destroying data on computers at Saudi Aramco, the Saudi Arabian state oil company and one of the world's largest corporations by market capitalization. The attack was straightforward compared to Stuxnet's elaborate precision, more a sledgehammer than a scalpel, but its effects were devastating in their immediacy. Shamoon overwrote the master boot records of approximately 30,000 computers, converting them to unusable machines displaying an image of a burning American flag on their screens. It destroyed the data on those computers' hard drives, wiping files that included operational records, communications, and years of accumulated data. Saudi Aramco's operations were disrupted for weeks as the company replaced hardware and rebuilt systems from backup, a process that required flying in hundreds of replacement hard drives from several countries because the supply of available units in the region was not sufficient. The message embedded in the image Shamoon displayed, the burning flag, and the name chosen for the virus, believed to be derived from the Arabic word for poison, were nakedly rhetorical. This was not a carefully targeted intelligence operation designed to achieve a specific, deniable sabotage objective. This was an attack whose political statement was at least as important as its technical effect. Iran, or a group sponsored by Iran, was demonstrating that it could inflict substantial economic damage on the infrastructure of countries in the American alliance structure in the region. Saudi Arabia and Iran were engaged in their own overlay of religious and geopolitical competition, but the choice of an oil company, in a country that was closely allied with the United States, carried a clear message about the scope of Iranian cyber ambitions. Attribution for Shamoon was not immediately or definitively established in official statements from the affected governments, but American intelligence agencies concluded internally, and eventually leaked to journalists who reported it, that Iran was responsible through a group they called the Cutting Sword of Justice, which had publicly claimed credit for the Aramco attack. The conclusion was based on analysis of the malware's code, the infrastructure used to coordinate it, and the intelligence context about Iranian offensive cyber capabilities and intentions. Subsequent years would add further evidence. The Shamoon attack was followed by a second wave in 2016 that used an updated version of the same malware, and researchers found technical connections between the two Shamoon campaigns and other operations attributed to Iranian actors. The attack on Saudi Aramco was followed, in the autumn of 2012, by a distributed denial-of-service campaign against several major American banks, including Bank of America, JP Morgan Chase, Citigroup, and others. These attacks, known in the security community as Operation Ababel, flooded the bank's websites with enormous volumes of junk traffic, making the sites unavailable to ordinary users for extended periods. The attacks were attributed by American intelligence and cybersecurity officials to Iranian actors operating through a group calling itself the Izz-ad-Din al-Qassam cyber fighters. Unlike the destructive attacks on Saudi Aramco, the bank attacks were disruptive rather than destructive, causing reputational and customer service problems rather than permanent data loss or physical damage. But they demonstrated a willingness to attack the financial infrastructure of the United States directly, in ways that commanded significant attention from both the banking sector and the national security establishment. The pattern of Iranian cyber activity in this period was being tracked in real time by security companies and government agencies, and what they saw was an actor that was developing capability faster than most observers had anticipated. The Iranian program was not yet at the level of American or Israeli or Russian offensive cyber operations in terms of technical sophistication. But it was advancing steadily, learning from each operation, adding to its toolkit, and displaying a strategic audacity that suggested it was being directed by people who had thought carefully about how cyber operations could advance Iran's broader strategic interests. General Keith Alexander, who served as the director of the NSA and the commander of U.S. Cyber Command through this period, gave public testimony to Congress in 2012 in which he warned that Iran's cyber capabilities were advancing rapidly. He specifically cited the Aramco attack as evidence of Iran's willingness to use destructive cyber operations and as a warning about what more sophisticated Iranian operations could accomplish if the current trajectory continued. Alexander was careful in what he attributed publicly, but the Senate and House committees before which he testified received a considerably more detailed picture in classified sessions that followed his open testimony. What Stuxnet had set in motion was not what its designers had intended. The intended consequence was a setback to Iran's nuclear program, bought at the cost of burning valuable intelligence equities and deploying a novel weapon whose full implications had not been worked through. The unintended consequence was the creation of an adversary that was now an active, capable, and motivated actor in exactly the domain where the United States had believed its advantages were most significant. Iran had entered the cyber arena with a grudge, a demonstrated target list, and an acceleration of investment that Stuxnet itself had partly motivated. The lesson it had drawn from the evidence of its own centrifuge hauls was that cyber operations worked, that they could cause real harm, and that a country willing to invest in building the capability could reach its enemies through this domain in ways that its conventional military disadvantage would never allow. There is a question that historians and policy analysts have returned to repeatedly in the years since Stuxnet became public knowledge. A question that admits no clean answer and that gets more complicated the more carefully you examine it. Did it work? And if it worked, was it worth it? The first part of the question, about whether Stuxnet accomplished its immediate objective, has a cautiously affirmative answer. The evidence that the operation damaged Iran's enrichment program is substantial. The IAEA production data showed meaningful disruption. Expert analyses of the centrifuge counts and the enrichment output figures during the period of the attack consistently suggest a real and measurable effect. Iran's own acknowledgments, oblique and defensive as they were, conceded that the program had experienced difficulties. The most credible estimates of the delay imposed on Iran's program cluster around 1 to 2 years, a period during which Iran was commissioning fewer centrifuges and accumulating less enriched uranium than the theoretical capacity of its installed equipment would have produced in an undisrupted operation. For the intelligence strategists who designed and authorized the operation, this was worth having. 1 to 2 years was time for diplomatic processes to continue, time for sanctions to produce political effects, time for the internal politics of the Iranian government to evolve in ways that might produce negotiating flexibility. Whether those years were used effectively is a separate question, but they were real, and they were bought at a cost that was significantly lower than the military alternative would have imposed in blood, money, and regional destabilization. The second part of the question, about the worth of the operation in its larger consequences, is where the analysis becomes genuinely difficult. The designer of a new weapon class cannot reasonably be held responsible for every subsequent use of that weapon class by every actor who observes the original deployment and draws their own conclusions. But the connection between Stuxnet and the subsequent proliferation of destructive cyber weapons in the world's conflict landscape is not a theoretical association. It is a direct causal chain that runs through the incentives it created and the models it provided. The years following Stuxnet's disclosure saw a rapid acceleration in the development and deployment of destructive cyber capabilities by a range of state actors. Russia, which had already demonstrated a willingness to use disruptive cyber operations politically in the 2007 attacks on Estonian infrastructure and the 2008 Georgia conflict, developed and deployed capabilities that caused damage at scale Stuxnet had not approached. NotPetya, released in 2017 and attributed to Russian military intelligence, was nominally targeted at Ukrainian infrastructure but escaped in ways that caused an estimated $10 billion in global economic damage, destroying data at companies ranging from Danish shipping giant Maersk to American pharmaceutical manufacturer Merck to the delivery company FedEx. The operational model of a cyberweapon causing real economic destruction at scale, demonstrated first by Stuxnet, had become a strategy deployed with far less precision and far fewer targeting constraints. North Korea, operating with cyber capabilities that exceeded what its poverty-stricken conventional defense establishment might have suggested possible, deployed the WannaCry ransomware in 2017, a weapon that propagated globally using exploits developed by the NSA that had been leaked online. WannaCry hit hospitals, including the British National Health Service, in ways that disrupted patient care and, in disputed accounts, may have contributed to patient deaths. The tool that WannaCry leveraged, an NSA-developed Windows exploit called Eternal Blue, had been stolen from NSA systems by a group calling themselves the Shadow Brokers and published online, representing the most consequential known compromise of American offensive cyber tools to date. The chain of causality from Stuxnet to WannaCry ran through the weaponization of operating system vulnerabilities, the demonstration that such weapons could cause real-world harm, and the global awareness that the world's most capable states were sitting on precisely these kinds of capabilities. The arms control framework applicable to conventional military weapons had no satisfactory equivalent in the cyber domain. Nuclear weapons were governed by the Non-Proliferation Treaty. Biological weapons were subject to the Biological Weapons Convention. Chemical weapons came under the Chemical Weapons Convention. These frameworks were imperfect and frequently violated, but they established international norms that constrained state behavior and provided the basis for diplomatic pressure against violators. The cyber domain had no equivalent regime. States could claim any particular cyber operation fell within acceptable norms of espionage, which had long been considered an activity not governed by international law, even when those operations crossed into sabotage, as Stuxnet unambiguously had. The difficulty of attribution in cyberspace further undermined any enforcement mechanism, because a state that could credibly deny responsibility for an attack had strong incentives to do so. The governance deficit in cyberspace, a deficit that Stuxnet had both exploited and exposed, generated a decade of intensive discussion in international forums about whether and how the laws of armed conflict applied to cyber operations. The Tallinn Manual, produced by a group of international law experts convened by NATO's Cooperative Cyber Defense Center of Excellence and published initially in 2013, was the first serious attempt to apply existing international law principles to cyber conflict. Its analysis of Stuxnet, conducted on the basis of publicly available information, concluded that the operation likely constituted an act of force under international law standards because it caused physical damage, and that it potentially crossed the threshold into an armed attack, which would have implications for Iran's right to respond under self-defense principles. These legal conclusions were controversial and debated by governments whose own operations would have been implicated, but they established a framework for analysis that subsequent discussions built upon. The question of whether Stuxnet ultimately helped resolve the Iranian nuclear issue requires looking at the full arc of events. Iran continued enriching uranium after Stuxnet was discovered and after the immediate operational damage was repaired. The Islamic Republic responded to the pressure with a combination of defiance and eventual negotiation that produced, in July 2015, the Joint Comprehensive Plan of Action, the nuclear agreement that limited Iran's enrichment activities in exchange for relief from the international sanctions regime. The JCPOA, as it became known, represented exactly the kind of diplomatic outcome that the proponents of covert action as an alternative to war had hoped to create conditions for. The delay bought by Stuxnet, combined with the accumulated economic pressure of years of sanctions, had apparently contributed to a negotiating environment in which Tehran judged an agreement to be in its interest. Whether this outcome was durable proved to be a different question, one settled in 2018 when the Trump administration withdrew the United States from the JCPOA. Iran resumed portions of its enrichment activity in response, and the diplomatic architecture that had taken years to build came apart with a speed that sobered anyone who had believed it represented a permanent resolution. The centrifuges that Stuxnet had destroyed had been replaced. The cascade halls had been repopulated. Iran's enrichment capacity recovered and, in time, exceeded what it had been before the attack. The technical damage was undone. Only the political and legal framework that might have constrained the program's direction had proven to be fragile, and that fragility was not something any cyber weapon could have addressed. Looking back at the buried halls of the Natanz facility from the distance of more than a decade, what stands out most distinctly is not the sophistication of the weapon or the cleverness of its delivery mechanism, remarkable as both were. What stands out is the clarity with which Stuxnet drew a line between the world before it and the world after it. Before Stuxnet, cyberwarfare was largely theoretical at the level of physical destruction, a threat that security researchers modeled and governments quietly developed but that had not been demonstrated against real infrastructure in a real conflict. After Stuxnet, it was a documented, analyzed, publicly acknowledged matter of historical record that software could be made to destroy machinery, that the digital and physical worlds were not separate domains but intimately connected, and that the vulnerabilities of one were the vulnerabilities of the other. The engineers at the Idaho National Laboratory who tested centrifuges against code, the NSA operators who designed the spreading mechanism, the Unit 8200 specialists who contributed their expertise to the attack payload, the policymakers in Washington and Tel Aviv who authorized the operation. All of them understood they were doing something new. They may not have fully understood how new, or how lasting the changes they were setting in motion would prove to be. The weapon worked exactly as intended at the specific target, for the campaign period it was designed to run. Everything else that followed was the world adjusting to what they had shown was possible, a world in which the barrier between the network and the physical, between the screen and the machine, between code and consequence, had been permanently removed. The centrifuges are long since replaced or gone to scrap. The code is still out there, in malware databases and analysis archives and the institutional memory of every security organization that studied it. And the frontier it opened has never closed.